Right, so when we look at Fibonacci, we're going to do a little new thing first, and that is the strong induction. Now, I'm really happy with this honors pre-calc. We start teaching you math induction in ninth grade, some of you in 10th grade, and strong induction is a little extension of it. It's a little bit higher quality proof. It's not really going to seem like it does anything, though, but it's something you have to add to your consideration. It is including more conditions, but here's what happens. To get the strong induction, we still do P1 is true, and we essentially do the PK plus 1 is true. But what we add to it is that we're analyzing PR. All of the PRs where R is less than or equal to K, and that is going to be the difference between saying all of these are true as well. So when we said P1 is true and then PK plus 1 was true, that's the weak induction. The part we add to it is that P1, P2, P3, all the way to PK is true. So that's the difference. Yeah?
Can you put balance on R, or does this then only work for stuff where it's because for it's true for the n equals 1? Like, are you allowed to start at n equals 7? Because it's like PRs.
Oh, absolutely.
Okay.
Absolutely. You can start right. You can start at any value, but it's going all the way up to PK. So we used to just say PK. The assumption step was n equal to k, and you'd say true for n equal to k. Well, now we're saying it's true for n equal to up to k, which is the strong condition. Yeah.
If some proof works with weak induction, also works at strong induction?
That's a good question. I would say probably not. And so we're covering our bases better with this one. The only thing is I don't feel like we're doing anything different. We're just saying this. But I guess in some of the fancier, higher level proofs, you might be doing a little more with this 1 to k thing. And then Fibonacci is a sequence that uses recursion. And it's too bad we're not in 1500. I have a picture in 1500 that has, have you seen this thing before?
Oh.
And I don't know, I'm not drawing it very well, but it's the Mandelbrot set. That doesn't look like it? It looks like a turtle that was run over on the road. But anyway, the Mandelbrot set is if you take the -1 to 1, I, -I to I, if you take all the complex numbers and take a complex number like 1/2 plus 1/2 I, that's this one, and you square it, okay? Then put that in and square it. Then take that answer and square it. If you kept doing that, doing that like 50 times, sometimes it'll just go to infinity. But some of these, and I think this is one of them, will stay between 0 and 1. And what this Mandelbrot did is he took that answer and he said, I'm going to color that black. And then he'd take something like 1/2 plus, or maybe did 1/2 plus 1, let's say 1/3. And then he checked that one out and squared it, and that stayed between 0 and 1. So he filled that in. And you just keep doing that with all the points really close to it, and he ended up with this amazing pattern which we call fractals. So that's where fractals came from. It's from a recursion formula that settles between 0 and 1. And if you look at the pictures, you see dazzling pictures of fractals. Those are complex grids, and instead of all being one color like black, then they might say, oh, between 1 and 2 we're going to color it blue, and between 2 and 3 we're going to color it orange. And you can, when you're done, you get this dazzling picture. There's a lot of cool things with this. If you zoom in, it's like a jungle. You zoom in and you see more Mandelbrot sets. Zoom into those, you see more. And pretty interesting mathematics. and I'm actually putting together my second lecture on my 4D show. I'm still going to do that, and you guys will get to see it. And then in the spring, I'm going to do a chaos theory one that's going to have some of this in there. And I haven't got it done yet, but it's going to be fantastic, I hope. So Fibonacci uses this recursion idea, and it's not chaos yet, but it's building toward it. And what he said is that if you take f of 1, f of 2, and f of n plus 2, the next one is going to be the sum of the previous two, f of n plus 1 and f of n. So if we start f of 1 is 1, f of 2 is 1. This formula says the next one, f of 3, is going to be the previous one, f of n, f of 1, which would be 1, that's this one, plus f of 1 plus 1, which is f of 2. And so f of 3 is going to be 2. F of 4, that's when n is 2. Then you're going to get f of 3, which was 2, plus f of 2, which is 1. So this is going to be 2 plus 1. And you can see how that pattern would work. These symbols are going to be important when we prove things with Fibonacci. So that's what this whole unit's centered around, is doing math induction with Fibonacci. So here's the sequence. We're going to take a formula, and notice there's 3 parts to it. There's an an part, there's an an plus 1, and an an plus 2. See those 3? I'm sorry, an plus 1 and an an minus 1. an minus 1. So could you figure out what the next term is going to be? A of n plus 1. Well, let's see. If a of, let's say this is going to be 3. So we're going to do a of 2 plus 1, or a of 3. A of 2 plus 1. What's a of 2 squared? 4. 2 squared is 4, right? And then this one's just going to be a of n minus 1 would have been a 1, which is going to be 1. So what's 2 squared over 1? 4. And then you take the previous one, 4 squared over 2, and that'll be 8. 8 squared over 4, you'll get 16, and so on. This recursive formula could be reduced to something way simpler. What do you think it would be? This is 2 squared. This is when n equals 3. This is 2 what? Cubed when n equals 4. This is 2 fourth when n equals 5. So what do you think the formula is going to be? A of n is going to be 2 to the what? N minus 1. Instead of this whole mess here, which is descriptive, and it works with Fibonacci, we can reduce it to the a of n is 2 to the n minus 1. We got to prove it, though. So how are we going to do that? Math induction. So here goes. First step, and I'll highlight the first step. First step we're going to do like we always did. N equal to 1. 2 to the 1 minus 1. What's 2 to the 0? 1. Was that our first term? Yeah. So then we would say true for P1. Now's the part that's kind of fun. You're going to assume there's an A of R. So instead of AK, we're going to say A of R equal to 2 to the R minus 1. And then you got to say what R is. R is less than or equal to K. So before we just said AK would have been equal to 2 to the K minus 1. That's what we just said before. But this time, we're going to change it to R, and then tell us what K is. R is less than or equal to K. So we're going to go AR again. I'm going to use my blue highlighter. AR. And just R is going to be 1, 2, 3, 4, all the way to K. This is that new strong induction step. Make sure you highlight it or whatever it takes to notice it, because this is the part you're going to be a little confused with because it's new. And this is the strong form for induction. So now we're going to prove this, and this is going to be way easier than a lot of the things we've done. According to the formula, a of k plus 1 is going to be equal to a of k squared over a of k minus 1. But we're saying a of k is what? 2 to the k minus 1. So let's get rid of this. And we're going to say, oh, instead of a k squared, we're going to say 2 to the k minus 1 squared. And instead of a k minus 1, we're going to say 2k minus 1 minus 1. Am I losing anybody? Caleb, we good? All right. So then I'm just going to double this k minus 1 and get 2 to the 2k minus 2. 2 to the 2k minus 2 over 2 to the k minus 1 minus 1. Do you see where it's 2k minus 2? And then I'm going to do a little algebra help here. 2 to the 2k times 2 to the negative 2 over 2 to the k times 2 to the negative 2. What happens to the 2 to the negative 2's? They're out of there. And what's 2 to the 2k over 2 to the k? Very good. So there you got it. And 2 to the k is interesting because 2 to the k is interesting because if you go a to the k plus 1, this is just going to be 2 to the k minus 1 or plus 1 minus 1. And what is that? 2 to the k. So therefore it's true by math induction. This isn't super helpful because it's already worked out, but I just want to show you the flow and especially how this part works. So therefore it's true for P1, it's true for R equal to 1 through k, and R equal to k plus 1, then it's true by math induction. So now we're ready to do one of our own. You ready? This is going to be good. We're going to do one, and I'm just going to give you 2 to work on over the weekend. That's it. So I think that'll be plenty. If a sequence is defined like this, a of n plus 2 equals a of n plus 1 plus a of n. This is my recursion formula. And then this is my shortcut. And we like shortcut formulas, don't we? It's way better. So we want to show that this shortcut formula works for this situation. So we're going to start. N equal to 1. And n equal to 1, a of 1 needs to be less than 5/3 to the 1. And is a1 less than 5/3? Yep, true. For n equal to 1. Are we okay with that? Yes, Jake.
Will it always give us the shortcut that?
So now we do n equal to r, where r is less than or equal to k. And a of r is less than or equal to 5/3 r, where r equals 1, 2, 3, ... to what?
R.
Close, k. This is the strong induction part. Normally we just substituted this a of k equals or less than or equal to that with a k. Remember that? It's the same thing except we got to just state that n is equal to r, define r, and then we're good to go. That's the strong form. And you can argue with me because I don't know what difference it makes as far as the actual proof, but we're saying something a little bit more precise. And then we're ready for n equal to k plus 1. Now this step, with this one, now what you're going to do is you're going to go back to this part here that says a of k plus 2 plus 1 is equal to a of k plus 1 plus 1 plus a of k plus 1. And then this is equal to a of k plus 2 plus a of k plus 1. And what was a of k again? In terms of r? 5/3, right? So this is just going to be 5/3 to the k plus 2 plus 5/3 to the k plus what? 1. All right, now I don't know how you want to do this. I'm going to just do it this way. This is how many 5/3 to the k is this guy? 25/9. How many 5/3 to the k is this one? 5/3, right? You good with that? So if I took out a 5/3 to the k, what's going to be left here? If I took out this and 5/3, what's left? 5/3. What's left here if I took out a 5/3 and a 5/3 to the k? 1, right? Or 3/3. Are you okay with that? Okay. Now, what is 5/3 plus 3/3? 8/3. And what's 5/3? Is that right? 5/3? 8/3? Good. Yeah, that's right. And then this is 5/3 to the k plus 1. Got a little bit of revamping to do. No biggie. It's gonna be fine. Okay. Right now I have a of k plus 3 equal to a of k plus 2 plus a of k plus 1, right? Knock this down to a of k plus 1 because that's what we're trying to prove, right? The k plus 1 term. So if I subtract 2 here, I'm down here. What happens when I subtract 2 here? A of k plus a of k. Sorry about that. That's what I should have done in the first place. This is not helping. Okay? So once I have that, now a of k was 5/3 to the k. Correct? 5/3 to the k. And this is 5/3 to the k minus 1. If I take out a 5/3 to the k, I'm going to get 1 plus 5/3 to the negative 1. This works, will be a miracle. 5/3 to the k. What is 3/3 plus 3/5? Well, maybe instead of 3/3, let's just do it 5/5, huh? What's that? 8/25, right?
What is 8/6?
Or 8/5 to 8/5. Okay. And now, is this equal to, we want it to be a plus 1, right? A of k plus 1.